Hi, Deborah. Can you hear me?
Hello.
Hi, Deborah.
Hi. How you doing?
Doing well. How are you?
Okie dokie. Where are you?
Sweet. I'm over at my girlfriend's house.
So New Jersey still?
Still Jersey, yeah.
Yeah.
I'll be in Jersey for the next few months.
Oh.
Yeah.
Oh.
And then probably after that, moving to Florida.
Well, good luck with that.
Thank you.
Do you have a job lined up there?
Pretty close, yes.
Okay. Fingers
Gonna be-
crossed for you.
Thank you. Appreciate it.
Sure. So, I guess it's just you and me.
Yes. Stuart told us that he probably wasn't going to be here today.
Yeah.
Okay.
Yeah.
No problem.
Yeah. Let me just bring over my water.
Mhm.
Oh. Ugh. So the town of Jackson approved the observatory?
Oh, excellent.
I believe so. Speak to Sam.
Yeah, Sam had told me that they're hoping to break ground sometime in August. I think end of the summer.
Oh,
Yeah, like I think construction should be almost all the way through by the end of this calendar year,
oh,
apparently. Yeah.
oh. Well, I don't know what it is. An observatory as complicated as another building? Does it
I would
need
imagine it's even probably more complicated.
Mhm.
And especially building it on top of Snow King. Just like getting all the materials up to the top of the mountain is going to be quite a
Yes.
challenge.
Yes. Yeah. Well, you clearly need electricity, but do you need water?
I'm not sure. I think maybe even if they needed water, it could be done with like huge like tanks or bottles, not necessarily a plumbing system.
Yeah.
But yeah, it's really exciting, and I think next summer, if I'm available, because I'll be teaching in Florida, so I'll have the summers off.
Yeah.
I imagine that I'll be working in the observatory when it's up and running and we have people visiting.
Right. So, and I'm assuming it's more towards the back side, so you don't get the city lights, the town lights.
Yeah, exactly.
Yeah. Wait, let me see where the doggie is so I can let her out. She just finished dinner. Sue, do you want to go out? No, she's lying where she just wants to lie down. So, okay. All right.
So let's go to the slideshow here.
Yeah.
The screen.
No, not you go to the slideshow and I'm going to the door with the dog. So who do you see? Okay. So I'm assuming that this talk is going to be about black holes.
Yeah. When I was watching this movie, I was like, I don't know how much like science I can cover with this, but I did pick out three major points that were kind of cool. But this is more like trying to generate life in space. And to be honest, like I really wasn't a huge fan of this movie. I thought it was a little gruesome and a little
Yeah,
uh I don't know, uncomfortable at times. But
yeah, bizarre.
it really was bizarre, you're right. But it really got me thinking, and it's really cool that there is a Vsauce video out here that answers this question, is what would it be like if someone were born in space? It's kind of crazy to think about. When you think about every human that's ever existed on planet Earth, every one of them was born on the surface of the Earth, where gravity acts downward at a certain acceleration, 9.8
Yes,
meters per second squared. There have
yeah,
been a few people that have died not on the surface of Earth, so like above where space begins. And I think it's agreed that space starts about 60 miles above the Earth's surface.
yeah. That's where the Concorde used to fly, and they used to say it flew at the edge of space.
That's right. Yeah.
Yeah.
And
Yeah. So who died up there?
so I think it was one of the, I don't remember the mission. I mean, it's in the video here.
Oh, is that Sutter?
It could be, let me see. But yeah, I'll play this in a second.
Yeah.
What's interesting to note is like when human bodies are exposed to micro G environment, that is like in Earth's orbit, some physiological changes happen in the human body. For instance, bone density tends to decrease. Also, your spine decompresses a little bit, and therefore astronauts returning from space are a little bit taller than they were before.
I could use that.
Yeah. But also their hearts, their cardiac muscles shrink a little bit. And because
Right.
the heart does not have to pump against gravity.
Yes.
So if you're put in space for a long period of time, your heart can shrink, your bone density can go down, and your spine can elongate. But we want to explore what would happen if you had, so like in this movie, let's say a fetus develop in a microgravity environment. So he starts off a little bit off topic, but a couple minutes in, he gets to the question here.
Okay. Something happens to your eyes too.
Oh, that's right. Yes.
I can't remember. And that's not as reparable.
Yeah, I think it's maybe your lenses are like altered a little bit permanently. I'll have
Well,
to look
they
into
could
that.
be. And also the radiation, we get cataracts because of UV radiation.
Yes.
So when you're in Florida, you be careful, wear your shades all the time.
All right.
And if you get regular glasses, get UV coatings on them. But the radiation in space also creates cataracts.
Yeah. Less protection without the atmosphere.
Yeah. People different. Speaking of gravity, I was seeing another science kind of website, and they were talking about gravity waves in water and clouds.
Well, I think gravity waves can exist anywhere through any medium.
And I guess it had to do with the density, with the varying density.
So they're probably useful media to detect gravitational waves, because what gravitational waves do is they actually warp space-time by a very, very little bit. And the way we like
Yeah,
detected gravitational waves by that black hole merger
yeah,
was we had laser beams set up that hit these perfectly smooth mirrors.
yeah, the
And we
LIGO.
noticed that, yeah,
Yeah,
one signal came in a little bit before the other. So that means the distance to the mirrors actually changed.
yeah. So does the space station,
Mhm.
this comes back to a question I asked about acceleration. Does the space station have any propellant other than positional, adjustment jets?
Not
It
for the most part. The space
it
station is always falling towards Earth, but it has this sideways velocity to it. And it's
tangential voltage. Yeah,
exactly the tangential component. And so
yeah,
it's traveling at like 17,000 miles an hour,
yeah,
but there's nothing impeding it. So it just keeps falling to the Earth and missing it. And it keeps missing it. So it's constantly accelerating toward the Earth, but
uh-huh,
it never will hit the Earth because it's it's got that sideways velocity all the time.
uh-huh,
Eventually
uh-huh.
it will encounter some little particles of matter, which
Yeah,
can slow it down by a minuscule amount, and then it's corrected as needed.
yeah. Okay. So the astronauts experience zero gravity, like being in the vomit comet in the parabola plane, because they're always fall, because the plane is falling and the space station's falling. Is that it?
It's almost like if you were standing in an elevator and you
Yeah,
cut the cable, you'd
yeah,
fall with the elevator. But
yeah,
inside the box, you would feel nothing. You'd be just floating around, even though you're
yeah,
racing towards the Earth pretty quickly.
yeah, yeah. I thought we would be talking about the Penrose, what, phenomenon, process? What was this?
Rose phenomenon?
Yeah,
Is that like with black holes?
yeah, because they mentioned in the movie that that's what they were going, that was the purpose of the mission, to
Oh,
investigate the Penrose phenomenon, which I hadn't heard of, so I Googled it, and then I didn't understand it.
yeah. The next slide we talk about that. So how to
Okay,
harness energy from a black hole, and black holes technically have negative energy, and it sounds kind of crazy, but when you dive into the mechanics about the electric field around a black hole,
uh,
it's not prohibited by physics to do such a thing.
yeah,
We will get to that. But
okay,
this is, yeah, what I want
okay,
to just
one,
look at is if
yeah.
we have a human embryo developing in space, what sort of characteristics would it have?
Well, how does gravity affect? Well, probably not differentiation of cells.
So here is
Good.
all the effects that a normal human encounters when they're put into a zero-G environment or microgravity. So like one is you get space motion sickness because you're not feeling the regular gravity that you do every day. And the reason you get motion sickness, and this can happen if you're in a car, if you're on a fast spinning merry-go-round, or somebody spins you around really quickly. The reason you get sick and you want to vomit is what's happening is your body is reacting to this strange acceleration because their vestibular system in your inner ear senses this imbalance. And it's very similar to what you experience if you eat poisoned food. And you get the same response. It wants to reject whatever went into your mouth. So it's like a survival mechanism. The reason we get sick when we're spun around is our brain thinks that, oh, we just swallowed something poisonous. So that's just one of them. I mean, it's a proposed hypothesis, I should say. It's one of the widely accepted explanations for why we get motion sick.
Not that I have heard of medically.
What have you heard of?
That it's like conflicting signals of, for example, what your eye sees versus what your vestibular canals are sensing. And your vestibular canals are literally like gyroscopes. They're 3 semicircular hoops with little hair nerve endings with little, in essence, stones that brush against the hairs and give a feedback to the brain, because those hairs are really nerve endings, of your position, the way a gyroscope would. But your eyes usually are in sync with as we walk in gravity, your eyes confirm, well, but they've learned to, because the brain learns. You're not born with anything. You're not even born being able to see. Your brain learns to see from your eyes, which is one of the reasons they correct, like wall-eyed kids early, because they have to teach, because otherwise the kid learns to ignore one eye. It's the only sensible thing to do. But because the brain is getting mixed signals. So when you don't have gravity, with your eyes and your vestibular systems are 2 different things that are giving conflicting information.
Yeah, definitely, I agree with that.
Yeah.
What do you believe is the reason the body responds by trying to reject
nausea?
what's in the stomach? Yeah, why is nausea occur when there's a disagreement between the vestibular system and your optical input?
My guess is that it has to do with the vagus nerve, that somehow there's a feedback into the vagus nerve, which controls that sort of thing.
But it's interesting. I may pull it up after the rest of this video. But as you can see, like in this flow chart, it seems there is like a chain reaction of events. So space motion sickness can lead to altered body metabolism, because you know what? If you feel sick and you don't feel like eating, like that could throw off your eating cycles, and that, you know, may affect your metabolism, and then
Well,
your metabolism
it's
affects
that,
your
but it's
hormones
also,
and so on.
it's the neuroendocrine feedback system too. You know, our desire to eat, or all sorts of things. There's a communication between our neurological system and our hormonal excretion system. So yeah, there, you know, there it is right in the middle, altered endocrine.
And then apart from that, like completely
Yeah.
disconnected,
Yeah,
but eventually it looks like it converges, is when you're in zero G environment, there's nothing putting a load on your bones and joints and your
yes,
muscles. And so
yes,
your muscles realize, okay, I don't have to fight against gravity anymore. I don't need that
yeah,
much more muscle. And
yeah,
you have atrophy.
yeah.
And then of course,
And you would,
bones get less dense.
yes, but that might affect bone growth in you know, a child. You know, if somebody was born in zero G, because bones grow not only as they grow, but also in response to muscle use. Like a kid with polio, if you know, if in the days of polio, if a kid got it in his leg early, that bone would be shorter than the other leg.
Yeah,
Yeah,
definitely.
it's not just the muscles that would be atrophied.
Yeah, of course, bones as well.
Yeah, yeah.
So here.
Yeah. It would take me forever to do that. I can barely be on a boat. Yeah.
So it's just a common belief. I mean, there could be other just as valid hypotheses.
Yeah. This guy is a little loosey-goosey.
Mhm. Yeah.
Yeah.
What they did with rats is they actually gestated them in space. So pregnant rats were taken into space, and then their offspring were compared to those on Earth. And what happened was really interesting. When the mice were thrown, or the rats were thrown into a pool of water, is they had trouble getting themselves right side up.
The ones from space.
Mhm.
It may not matter to them what's right side up, because
Exactly.
it never mattered in space.
That's right. Yeah.
Yeah, this is the thing.
Mhm.
Yeah, see, I mean, he's equating apples and oranges here, so don't believe everything he says. See, so one thing I didn't understand about the movie, and one of the characters says, "Why are you making all these babies? They're going to die from the radiation anyway."
Yeah.
Not to mention that she kept the kid in an incubator. I mean, what? I mean,
Right.
yeah. It took our boy, what was his name, to get the baby out of the incubator and be taught to be a human being, to speak, to walk, to love, to laugh.
Hmm.
Yeah.
Yeah, and it would be really hard to try to nurture somebody in such an environment that's never been done before.
Right. But he knew, even though he wasn't nurtured himself, and psychologically, she
Right.
didn't know. She was kind of a Medea character, killing her kids and her husband.
Mhm.
That was her crime.
Right.
But all she can do is try to make babies. To what? To die. But then the question is, what's the radiation in space?
Yeah, and it depends, like, how far away you are from the sun or another source of light.
Yeah.
As you venture farther away from the sun, radiation becomes less intense. So,
Yes.
I mean, it could be argued that they were at a safe distance, but even still,
Yeah.
you have cosmic microwave background radiation also, and
Yeah.
stuff from distant objects.
Yeah. Well, things that our atmosphere filters out.
Right.
Right.
Exactly. Mhm.
Yeah. Because they talk about that's one of the issues of space, prolonged flight to Mars, or Elon Musk's roadster deteriorating just from the radiation.
That's true, of course. And now I wanted to move on to this Penrose phenomenon. It's like how you can extract energy from a black hole. Black holes are really interesting because the things that orbit around the event horizon
Yes.
have massive potential energy wells, basically. So
Yes.
the potential energy from just like 1 centimeter above the event horizon to like half a centimeter, that little drop, half a centimeter drop, is tremendous, because the gravitational well, if you think about it like that, is so incredibly steep.
Yes.
So what I found, and this is something that I learned, well, here, we'll start with this first. Roger Penrose theorized that particle disintegration, and this is sort of like the Hawking radiation, you could draw energy out of the black hole. And it's a little bit complex to understand, and I think even harder to explain. Because I've read about this several times, and I remember doing like one of the mind-bending astronomy videos a while back over the summer, and I talked about Hawking radiation. And it goes like this: you have two particles that are virtual, so they just pop into existence from nothing. What usually happens is they annihilate each other and go away like nothing ever happened.
Yeah.
But sometimes these virtual particles appear near a black hole, and one of the partners drops in below the event horizon and the other one doesn't. The
Ah,
other one is just free to roam away. And now you have a forsaken particle that does not have a partner.
yeah.
And what this looks like is particles being emitted from the black hole. And it's really strange because nothing comes out of a black hole. We didn't break any rules here. We didn't break any rules because the particle that is ejected from the black hole was there the whole time. When it popped into existence and it just didn't annihilate with its partner, it just floated away.
Well, what about energy cannot be created or consumed, or
Yeah. And
so had a particle just suddenly pop into existence out of nothing?
yeah, so it's like now you have this anti-particle or particle. You have
Yeah,
this virtual matter floating around in space, and it's like an energy debt. It's like an energy deficit. The universe has to pay it back, but it's inside of a black hole. You can't retrieve it yet. You can't retrieve it yet. Eventually, over eons, and I'm talking about like 10 to the 10 to the 10 years,
yeah.
some of the black holes will evaporate. And when that happens, okay, now the particle that's left can annihilate, and then we're back to zero.
Okay, so this goes to a whole other question. The ultimate fate of a black hole. They can evaporate, they can just, not to mention what happened to all the matter that got gobbled up inside,
Right.
but there can be what, annihilation. I don't mean annihilation as in some other force, but an end to a black hole.
Yeah. And the end of the black hole is not for an extremely long time. So here, 2 times 10 to the 100 years.
Yeah, that's a while. Yeah.
And so
That black hole evaporation, particles escape. Well, I can read, I can find this. So is this just theoretical, or do you think that this is actually possible?
it makes sense, but I don't think it's been experimentally confirmed.
Mhm.
But if you go through the science, you work out the math, you don't have any violation of physics going on.
Uh-huh.
So it's legitimate, but I don't think we've ever observed anything close to this happening.
Uh-huh.
The closest we've ever got to studying black holes is just capturing an image of it, an image of the accretion disk around it from
Okay.
thousands and thousands of light years away.
Right. I know the
To
image.
think that we would be able to study individual particles roaming around the ring of the black hole is crazy.
Yeah.
I don't know if we'll ever be able to do that, to be honest,
Right.
because of just how large our Milky Way is and how long it would take to travel toward the center is
Mhm.
unimaginable.
Right. But you see depictions of black holes with jets coming out.
Mhm.
And is that meant to be the Hawking radiation?
It's not. That is something completely different. So the astrophysical jets that you see being shot out of a black hole
Yeah.
is matter and radiation that got really, really close to being sucked in, and at the very last minute was flung out because of the incredible potential energy it had. So it's sort of like being spun around at an extremely fast rate and then let go.
Yeah. Okay.
So those jets don't come out of the black hole, they come out of the ring around it. So nothing ever fell in to begin with.
Okay.
Try to find
Okay.
a
So
little
now,
picture of
so
that.
Hawking.
Yeah.
Oh, there you go. Astrophysical jet. That's what it's called.
Mhm. And so this is even beyond what I studied. I kind of just like brushed the surface of this in graduate school when I did when I studied high energy astrophysics.
Yes.
But I think what happens here, if I'm reading this correctly, is the magnetic field that's associated with the black hole kind of disrupts this rotation of the matter and shoots it out
Yeah.
perpendicular to the plane of the black hole.
Yeah. So, yeah. So,
And so
okay,
here,
so
look,
what,
we're back to the Penrose mechanism, where this,
okay, yes, I was gonna say, take it back to the Penrose mechanism.
yeah.
Um,
So this rotation, the energy of that rotation can be harnessed.
yeah. So just to get back to this bizarre movie, in the
Mhm.
end, father and daughter get in the shuttle to go into a black hole or towards a black hole.
Right.
Was that it?
Yeah. So, and I think what happened before the end of the movie, or like just before the end, was I forget the name. One of the characters was like actually sucked into the black hole, and we watched her get
Yes.
stretched out.
Spaghettified. Yeah.
Spaghettified, right?
Yeah. Yeah.
Which was actually what I was going to go into the next slide.
Okay.
But yeah, Hawking radiation is an extremely complex topic. And you made a really good point. You said how energy is never created nor destroyed. How is it that we have stuff flying out of black holes and black holes being like these lock boxes where something gets sucked in but never comes out?
Yeah.
And we've never, and we probably will never see anything come out of a black hole. And for us humans, black holes are an eternal lockbox. But whoever is around, whoever can stick around to see the end of the universe, will hopefully observe all of the energy in the universe being conserved.
Yeah. Yeah. And then what literally happens to those leptons and in the center of the black hole. Stuart is all over this kind of stuff. It's a shame he's not here to contribute, because it doesn't seem when he's participating, doesn't he seem like he really is
Absolutely.
into this?
Absolutely. Yeah. I think he's blown away by black holes just as I am.
Yeah.
And I've always been interested in just like what happens to the universe after so many years. So I think we took a look at this article, Timeline of the Far Future.
Oh,
and
yes, we
we
did.
scroll down to like quadrillions and 10 to the 1,000 years, and we find that even the basic building blocks of matter, like protons, will eventually vaporize into nothing.
Well, one might think that the Big Bang had to come from something, so maybe they're compressed into something that will bang again.
That's right. And that is, look, that is the very, very last event.
Yeah.
10 to the 10 to the 10 to the 56
Yeah.
years seems to be the lower bound for which quantum effects may restart the universe.
Yeah. Yeah.
I think that's the wildest thing.
Yes. Well, but it makes sense because we were not in. We didn't happen out of nothing to have something now.
Yeah.
So
And this I would bet if Einstein were alive today and he read through this article, he would be pretty upset at what is written here, because it sounds like the entire universe and everything we know about it is just probabilistic. It's like, oh, well, there's a chance that this happens. And the reason anything exists at all is luck.
So there's one thing here. Estimated time for a Boltzmann brain to appear in the vacuum via spontaneous entropy decrease. That's the one, yeah. What the hell?
Yeah. Yeah. So a Boltzmann brain is like an actual being with a memory of having, it's like, oh yeah, I existed. And it's like having a new person just come into existence. Because you think about it, like, what is a human body? A human body is a collection of carbon atoms, hydrogen atoms, oxygen atoms, and so on.
Yeah.
And those atoms are just quarks and leptons. That's it. A whole human body, even the brain and its memories, are just quarks and leptons interacting with the four fundamental forces of the universe. And there's nothing to stop my exact arrangement of atoms to form somewhere else in the universe. And you can have an identical clone of me somewhere in Andromeda. It's not impossible.
The issue is the experience.
Because you think about, like, what is my memory? Like, the memory of my 21st birthday is literally just my synapses in my brain, which is just a lump of fat and water firing little electrons back and forth. That can totally happen anywhere else in the universe. I can have electrons and water molecules do the same thing elsewhere, and then I have another Ryan de Gregorio at the other end of the universe who also remembers my 21st birthday.
Well, from a physics point of view, yes, but from a behavioral point of view, your brain makes memories having lived through an experience or interpreted an experience.
Yeah.
So you in Andromeda, you will have had the same birthday party.
Well, of course, but my past self doesn't exist. My 21-year-old self is nowhere to be found and never will be. Like, Ryan de Gregorio at 21 years old is gone. The only thing that we have right here is my collection of atoms and my brain.
That's right.
And my brain is the only thing that has any memories.
Right, but it learned those memories, it garnered those memories from living through an experience. If you didn't live through that experience, whatever your 21st birthday was, it was not surfing off of La Jolla, right?
Yeah, exactly.
So you don't have those memories where the guy who was surfing off of La Jolla has those memories. So something about memory and the soul is a particular set of quarks and leptons.
Definitely.
Yeah.
But it's crazy to think about. I mean, I would
Yeah,
love to dive into this
yeah.
article. I could talk for hours. But the last thing I
Yeah.
wanted to
Yeah.
look
So,
at
but
was spaghettification. What happens when you get sucked into a black hole?
yeah,
Why does this happen? Why do we get stretched out to one atom thick, approximately?
yeah,
And it all has to do with tidal forces. So the same forces that govern the ocean coming in and out
yeah.
is the same thing that will tear anybody
Tidal.
to shreds if they come too close to a black hole.
It's not the tearing of by gravity.
It is
What's
gravity,
relationship?
but it's
Yeah.
a special phenomenon that occurs when gravity, the force of gravity acts in such a way that it's 4 times as strong on an object that's twice as close. So it works as 1 over r squared. If you increase your distance by a factor of 2, you decrease your gravitational pull by a factor of 4.
Yes.
And that's dramatic. And it's
Yes.
really, really dramatic when you get too close to a black hole. So let's say you were to float near a black hole and your feet were facing it. Your feet were close to the black hole's edge and your head was
Yeah.
back here. So you're falling in feet first.
Yeah.
The gravitational tug on your feet will be so much stronger, immense, pulling on your feet. And in comparison, your head really won't feel anything at all. And so
Yeah.
you get stretched
Yeah.
because your feet feel so much more of gravitational pull than your head. And the stretching is absolutely insane.
Yeah. Yeah.
Oops, that's actual spaghetti. What I was going to do is spaghettification.
Raznikov tube.
The
To go
noodle
back to
effect
the
also.
yeah.
The Penrose?
When I Googled it, because it is involved with the magnetic fields around a black hole, right? So
Yeah.
there was so what do we know about the so I'm going backwards here in your conversation, presentation. But what do we know about the magnetic fields around black holes?
Right. So magnetic fields exist everywhere. When you have charged particles in a magnetic field,
yeah.
Let me try to get this right. I want to explain it in a way that's a little bit pretty coherent.
I'm thinking in terms of
yeah,
auroras. Okay.
Right. Yeah. What I wanted to say was when you have charged particles in a magnetic field, they accelerate. And this acceleration can provide energy. I'm being very general, very vague about this. I'm not being specific at all.
That's the level I can understand. So thank you.
Yeah. So it's thought that you could harness this energy. You can let these particles smash into a generator of some sort. The same way you have wind energy or hydroelectric energy, you allow particles to hit something and you convert their energy. So air particles that hit wind turbines, translate into mechanical energy and you can spin a turbine. And the same thing works at the Hoover Dam. You have water particles sloshing into a wheel or some sort of turbine, and you're converting that lateral energy to rotational energy or whatever you want.
Yeah.
In the same way, you can take charged particles and now they're much, much lighter than the particles we have here on Earth that we're using for energy, but they're moving also. And you can make them hit whatever you want and transfer that kinetic energy into useful energy. Sort of the same way, like we were talking about the solar sails,
Yes.
how
Yeah.
the panels can capture radiation, and the radiation has some momentum to it, and you can push on a solar sail and you can make it move.
Yes. Yeah. Yeah.
It's something along those lines. Of course, I'm not very well educated in this kind of
Yeah.
part of physics.
Well, this is pretty highfalutin.
It is. It really is. And I don't know when or if we'll ever get to try this. You know, a lot of these articles, could we harness energy from black holes, are extremely far-fetched. They're not impossible, but as you said, really highfalutin.
Yeah. Truly theoretical.
Mm-hmm. Definitely.
Yeah.
But yeah, going back to
so spaghettification, yes.
Yeah, spaghettification is this animation, and this is kind of almost exactly like the movie. We have like an astronaut like that, and just being, you know, stretched thin.
Yeah.
So this is also called the noodle effect, I think. And this is really what tidal forces are. So we experience tides on Earth, and I think I touched on this maybe a couple meetings ago when we looked at like the tide calendar. Is you have like the moon, for instance, on one side of the Earth, and it's pulling the Earth more strongly on the side that's closer to it than it is from the side that's farther away.
Right.
And you get this squashing effect. And this is what displaces huge bodies of water, and you allow the tides to go in and out. It's almost like moving a boulder across a swimming pool. And you'll notice that as water is being pushed to one side and being like, and then receding from the other side.
Mm-hmm.
And so that's what's happening. You're, you can think relative to your feet, your head is receding and your feet are being pulled by the gravitational force.
Yeah.
And let me see. Oh, so spaghettification also happens with supernovae. So this is not the correct image, but it reminded me of a really cool phenomenon. Type 1A supernovae are the events that we use for standard candles. And this is how we know huge distances in the universe. When a supernovae explodes, it explodes with the same exact brightness all the time. And that's because you can only pile on so much matter onto a star before it can take no more and it rebounds and explodes. The way a type 1A supernova does that is you have a binary system. So you have usually like a white dwarf star, a really tiny star. And then you have its companion, which can be a less massive star, but also bigger. And the white dwarf is denser than its companion. And what can sometimes happen is the little white dwarf can act like a vampire, and it can draw material away from the larger star. And so let me actually find a good illustration of this.
And because it's denser, would you use the term gravity or tidal forces with that?
That's right. Yes. So it's got a stronger gravitational pull because it's denser. So
Yeah.
here's an animation, actually, I think. See if it plays. Oh no, that's not it. That's a merger. I want to find the one where it's, okay, this is it. So the progenitor of a type 1a supernova. So you have the yellow one, which is like a dwarf, and you have the red star, which is a giant. The red
Yes.
one, the giant one, is less dense. What happens is the little one robs material from the less dense star. And I think the bottom left square is the best way to illustrate this. So it's like it's sucking material out from the larger star.
Yes.
And there comes a point where this white dwarf star can take no more. It can't pile on any more mass, because any more it'll explode. And this happens at about 1.4 solar masses. This is also called the Chandrasekhar limit. And it's when the electrons in the core of the star get so smushed together that they can't be packed any more closely. And or otherwise they'll violate quantum mechanics, and we don't want that. So what happens is it explodes in this incredibly violent explosion, and it outshines entire galaxies. And it's always the same brightness because it's always the same mass. Since a star can never be more than 1.4 solar masses, or I should say a white dwarf can never be more than 1.4 solar masses, the explosion is always going to be of the same magnitude.
Yeah.
Yeah, sometimes you have like something that looks like this. You have like an accretion disk almost.
Yeah.
But it turns out it's quite rare that single degenerate progenitors are less than a fifth of all type 1a supernovae. Yeah, so those are the three points I wanted to hit, which were what's it like to be not only in space, but if you were born in space, the Penrose mechanism, which you can draw energy from a black hole's accretion disk. And then finally, what happens if you get too close to a black hole?
Yeah.
And yeah, it would have been nice to have Stuart here, because I think all of this he would be fascinated with.
He would be, and he'd understand it more and have ideas and contribute questions and thoughts, because he's really into it. It's funny, his daughter, when she was a little girl, wanted to be an astrophysicist.
Wow.
Yeah. Now she's off on international relations and now that she's in college, but it's I don't know, maybe he picked some up with her and kept running with it.
Yeah.
Yeah. The movie itself was bizarre, but
yeah, I was kind of like grossed out a couple times, to be honest.
Oh yeah,
it was hard to watch some parts, but
yeah,
I made sure to pick out interesting points of it.
Yeah. Well, yeah, I fast forwarded through a bit. Yeah, but fortunately I stopped enough to hear this or that made sense, that was interesting to talk about today. So
For sure. Yep.
Yeah. I don't know when Stuart will be back, but he is in America, but he's on vacation and he's working despite that remotely anyway. So he said he wouldn't be able to fit this in, but I don't know when he's coming back. Maybe it could be by next week.
Okay.
Yeah. So any thoughts so thank you for tonight, though.
Of course.
No. There's
Yeah, I think next week we will be watching, what did I put? I updated the website, Europa report.
Europa report.
Yes.
So
So
okay,
that
so that's
was
the 28th.
Yep, the 28th.
So is that on like Amazon or something?
Let me see.
How'd you find it?
On YouTube. It's on YouTube.
Okay.
Mhm.
I just watched a Hindi movie on YouTube.
Nice.
Yeah. Okay, Europa report.
Yep.
All right. Well, thanks, and take care there in New Jersey.
Of course, you
Did
too.
you have a little rain today?
We did. You did have some rain.
Yeah. We had a blue sky day
Nice.
out here. Yeah. And most of the snow is melted around my house. Thank God. Oh, well. All right. Well, say hello to the beach for me. Are you near the beach?
Yeah, we're about half hour away from the beach.
Go to the beach for me, would you?
Okay, for sure.
Stuart grew up near in Philadelphia, but near, the family had a place on the Jersey Shore in Ventnor. I never was there. That was before my time. So, but yeah, please, I need the beach. So you got to do it for me. Okay, good night.